Okay, so what I've drawn here is a manipulator without joining the links. I've only drawn the axis of the manipulator, right? So this is also, this distance is L1. Okay, so when I draw a cylinder with an arrow, it means it's a revolute joint. When I draw a box, it means it's a prismatic joint. It's a linear joint. And the axes show the direction. So this is D, this is theta. When I say theta, it's for revolute joints, really means that those are the axes which it rotates, right? So this is that, then this, let's just call this point the end effector. Okay, what does this mean to show it? It's actually there's a link like this. Okay, I have not shown the link because it's just going to make a lot of clutter, and then there is a link like this, and then this is also joined, but it just makes, it'll just add a lot of clutter to the figure. So I'm just skipping the links. So links are not shown, only the joints are shown. Okay, and I've also marked the distances. Now this manipulator has one revolute joint and has two prismatic joints. Okay, how do I identify that? Well, you can see there are two boxes and there's one cylinder. Okay, what you will see is that they'll abbreviate this as 1R 2P. So sometimes you'll see, if you see something like this, 1R 2P manipulator, it means that the system has one revolute and two prismatic joints. It's a very common way people talk about manipulators in terms of R and P. Okay, so for this problem, the problem is compute the position and orientation of the end effector using DH convention. Yeah, I'll just use the handout. So let's start with this. Okay, assign coordinate frames. So first, assign ZI along the axis of actuation for each link. So let's go here. Assign coordinate frames. So here's the first step. I need to assign Z axis along the axis of actuation. We'll start with Z0. This is Z0, Z1, Z2. Right? 3 joints, 3 axes. Okay. Done with step 1. Assign base frame OO, XO, YO, Z0. The Z0 has already been assigned. Assign X0 arbitrarily. Assign Y0 based on X0 and Z0. So what this is saying is, you can first assign X0. Now, obviously, X0 will be close to Z0. You have like infinitely many choices. You could draw it like this, like this. Like anything normal to Z0 is fine for X0. Okay, just choose one of them. So I'm just going to choose X0 to be this way. Okay, this is an arbitrary choice. Remember, it could be anywhere 90 degrees to Z0. Next step is assign Y0. So what we do here is we use the right-hand rule. X cross Y is Z. So if I curl my fingers from X0 to Y0, then my thumb of the right finger should point along Z0. And that only happens when Y0 is this way. Cannot be anywhere else. It can't be here, for example. This is not correct because it will not give me right-hand rule. Okay, so that's step 2. So we are done with this step. Now we go to step 3. This one is iteratively computing x1, y1, x2, y2, and so on. So we need to figure out a relation between zi minus 1 and zi, and use this relation to figure out which of these cases it lies, and then we'll follow the rules for that. So this is relation between zi minus 1 zi are not coplanar. You will see that none of the problems we talk about are actually going to fit in this category. You'll usually be this or this. Okay. So I would say by far you can just skip the step number 1. Z axes are parallel or axes intersect. Okay, let's see which of those two are valid for the first two pairs. First pair. So look at Z0 and look at Z1. Okay. Z0 and Z1 are, Z1 is this way, Z0 this way. Okay. Here is a case where Z0 and Z1 are intersecting. They intersect. So we use case number 3. So in this case, xi is chosen to be normal to the plane formed by zi minus 1 and zi. Okay. So what it means is, going back to this, it says that I need to assign x1 would be at right angles to z0 and z1. That's all. So if I want to assign x1 at right angles, I actually have quite a few choices. Since z0 and z1 is, so let me draw it slightly differently. Since z0 and z1 is in the same direction, they intersect. X1 can be anything in this plane. Right? It could be anything in this plane. You could choose any direction, because x1 follows the convention that it is 90 degrees to z0 and z1. Okay, however, you choose whichever, I mean, you can choose whichever you want. Just that I decided to go with this one. Okay, and for a very good reason. I wanted it to be parallel to x0 and make my life easy later on. Okay, but you're free to choose any direction, which is 90 degrees to z0 and z1. Okay, we assign x1. Next, we go apply that particular this part again. So again, I need to check the relation between zi minus 1 and zi for the next pair. So I look at z2. So z2 is this way. Z1 is this way here. So now the question is, what does it follow? So is it parallel or it is intersecting? You can see that Z1, if you extend Z1, it actually intersects Z2. So this again fits under the third one, Zi minus 1 Zi intersect. In this case, Xi is chosen to be normal to the plane formed by Zi minus 1 and Zi. So let's see what that would mean. Okay, so I'm going to draw Z2 this way, Z1 this way, and I'm told that X1 has to be, X2 has to be at right angles to Z1 and Z2. So there turns out to be two options. One is you could draw X2 like this, you could draw X2 like this. Okay, both are valid choices. You could use either of them. Okay, so I chose X2 to be this way, but there is nothing preventing you from taking it this way. I just chose it because I just like the fact that all my x's are lined up, and that will make my DH table kind of easier to populate. Okay, that's done. Next, we move to the next step, which is now something which I skipped here, assign yi. Says assign yi based on, so you could assign yi, but okay, so you could assign y1, y2 over here based on the right hand rule. But I'll skip that step only because when I actually populate the DH table, so if you look at this DH table, in this figure, this one, or this one, you see that I really don't need yi here. I don't need yi or yi minus 1. So it really doesn't really, I don't need to assign yi minus 1. And so just to save myself from some work and also some clutter in the figure, I will just skip yi. But you do not need to assign yi unless you need it for some other reason. So I'll just skip assigning yi. Okay. Okay, so final step. So we are done with this. I skipped yi, assigning yi. Finally, we need to attach an end effector frame. So that would be the last frame. Attach Zn to be in the same direction as Zn minus 1. Okay, so if you go back, say assign Zn, so it will be Z3 in the same direction as Zn minus 1. So Zn minus 1 is Z2. So assign Z3 in the same direction as Z2, which I did. And then I still need to assign X3. Now, depending on the relation between Zn and Zn minus 1, attach frame Xn. Okay, so where do I find this relation? It's back here. I need to figure out which of those two cases does it lie in. So look back here. We see that Z3 and Z2 are actually intersecting. And so if they're intersecting, then I need to follow number 3. In this case, xi is chosen to be normal to the plane formed by zi minus 1 and zi. So in this case, so z2 and z3 is here. And so really what can be done is you can look at this plane, which is 90 degrees, and you can assign x3 in any direction you want. Okay, any direction is fine. Now, to make your life simple, later on, I would highly recommend that you assign it such a way that it is parallel to x2. Okay, but you could assign it any direction normal to z2 and z3. Okay, again, you could assign y2 here, but I think it's just going to add clutter. It's not needed for our calculations. But if you want to assign y, there are clearly two options. One is this way, one is this way. One of them follows the right-hand rule, one of them does not. So the one which follows the right-hand rule is, I think, this way. If you do y3 this way, no, my bad. If you do y3 that way, it will not follow. If you do y3 this way, then x cross y, so when you curl your fingers from x to y, z3 is your direction of your right-hand thumb. So curl your fingers, right-hand fingers from x3 to y3, the thumb should give you direction of z3, and that's the right convention. Okay, so the way I do this is, well, there are two ways to do it. One is you could use what is provided in this figure. Okay, this figure basically tells you how AI, alpha, di, theta is assigned. And I just find that it's too hard to reproduce that figure in the exam. So what I do is I have my own way of doing this. And this edited as follows. Okay, I typically draw these two figures to help me figure this out. Ci minus 1, zi, xi, and then xi minus 1, xi, zi minus 1, alpha I, theta I. So this will be used to compute alpha I and ai. And this will be used to compute di and theta I. Okay, so let's do this. Okay, let's start this. So first, link I equals 1. Okay, so what we need is to compute ai alpha I, so a1 alpha 1. We need to basically, it will be, I'll put I equals 1 here. So we need the angle between, or distance between z0 and z1. So just putting I equals 1. and z0, z1, and x1. Okay, so what this means is we need to figure out the angle between z0 and z1 about axis x1. Okay, let's go here. Z0 is here, Z1 is here. I'll just draw it here so it's not in the clutter. And we want to find that when the angle alpha I is going to be the angle between Z0 and Z1 along x1. X1 is here, right? So angle between Z0 and Z1 along x1. So you can see that Z0 and Z1 are parallel to each other. And so the angle between those two is going to be 0. So from this figure here, alpha 1 equal to 0. Then we need to compute A1. That's going to be the distance between Z0 and Z1 along x1. So if you look at it, let's look at the distance between Z0 and Z1 along x1. So you need to find the distance along this axis. But since Z0 and Z1 along the same line, the distance is 0. Now, if Z0 was something like this, then the distance wouldn't be non-zero. This would be the distance between Z0 and Z1. But in this case, that's not true. They are parallel. So A1 is 0. So that's what we got from the first one. Next, we need to go with this figure. So to compute D1 theta 1, I'll put I equals 1, x0, x1, and I minus 1 is Z0. So I need to compute, I need to look at x0 and x1. Let's look at those axes. X0 is here, x1 is here, x0, x1, and then I also need Z0. Z0 is okay. Now let's figure out what alpha, theta D1 is and theta 1 is. So D1 is the distance between x0 and x1 along the Z0 axis. Okay. So distance between x0 and x1 along Z0 is basically this distance, and that is given as L1. So this was L1. Okay, and then we need to compute theta 1. It's the angle between x0 and x1 along the Z0 axis. Now, the way you see it is right now, x1 and x0 are on top of each other. So you need to look at this this way. You look at it down like this. So if you look at x0, the angle between x0 and x1 along Z0, you'll see that it is basically 0, but that is when theta 1 is 0. When theta 1 is not 0, you will see that x1 actually rotates, right? When theta 1 is not 0, x1 would rotate. It will be at a different axis, something like this. And that's because the manipulator, that is a degree of freedom. It's going to basically be moving. So you cannot say it's 0 because it's a function of theta 1. So the angle here is simply theta 1. Okay, theta 1 is theta 1. So that is basically the first line of the DH table. 0, 0, L1, theta 1. So I can go back and write it down in the table. 0, 0, L1, theta 1. Okay, so this is the reasoning. Okay, so let's put I equals 2. So we'll look at this figure first. So we have I equals 2. So Z 2 minus 1 is 1. Z2 xi is 2. And so in order to figure out di, sorry, alpha I, alpha 2 and theta A2, I need to look at the relation between Z1 and Z2. So let's see where Z1 and Z2 is. Z1 is here, Z2 is here. So let me draw that here on the side. Z1, it's up. Z2 is pointing to the right. Okay, here. And I also need another axis, X2. X2 is here. Okay, so the first thing is to compute, let's say, AI or A2. A2 is the distance from Z1 and Z2 along X2. So Z1 passes through the origin. And if you want to compute the distance along X2, then you can see that the distance is going to be 0 because Z1 actually passes through the origin. Okay, similarly, if you want to compute alpha 2, that will be the angle made by Z1 with Z2 along X2. Okay, so Z, for all practical purposes, Z1 is here. And we need to compute the angle between Z1 and Z2. So Z1 and Z2 along X is X2. Okay, now the issue is that when you go from, if you see this figure, you need to go from Z1 to Z2, right? Look at how the angle is. It's counterclockwise from Z1 to Z2. So here, if you want to go counterclockwise, you have to go this way. So this angle is 270 degrees. Okay, it's not 90 degrees. If you want to go clockwise, so there's another way you could do this. You could also go clockwise, like this is counterclockwise, but you could go clockwise, then that angle would be minus 90 degrees. So that both those angles are correct angles. You could either use the clockwise convention or the counterclockwise. Just be mindful that you need to put the right sign. So it's either minus 90 degrees or plus 270 degrees. So that's that completes, well, that gives me two elements. Let me get the next two. For the next two, I need to put I equals 2. So x 2 minus 1 is 1, x2, and then zi minus 1. So 2 minus 1 is 1. So I need to the relation between x1 and x2 along z1. So let's see where x1 and x2 is. X1 is here, x2 is there. So I'll draw it here. X1, x2. And then I also need axis z1. Z1 is up this way. Okay, so I need to, from this, I'm going to evaluate what d2 is and what theta 2 is. Okay, so for d2, it's the distance between x1 and x2 along z1. So x1, x2 along z1. So what's that distance? It's this distance. That's nothing but d2. So this distance is d2. So this d2 is d2. And then for theta 2, it's the angle between x1 and x2 along z1. Okay, so here theta is not a parameter. It is not that is a revolute joint. So this axis remains parallel to x1 no matter what. So if it remains parallel, this angle is 0. Okay, so angle between x1 and x2 along z1 is going to be 0 because x1 and x2 line up. So, or in other words, you look at it this way, and you'll see that they line up. So this gives me the second line of the DH. 0, 270 or minus 90, and then D2, 0. So 0, either you can put 270 or minus 90, both will give the same answer, D2 and 0. Okay, so here I equals 3. So let's do the first one. We want to compute A3, alpha 3. For that, I put I equals 3. So Z2, Z3 here, and I equals 3, so X3. So I need to find the relation between Z2 and Z3 along X3. Z2 is here, Z3 is here, Z2, Z3, and X3 is here. Okay, so first, the distance between Z2 and Z3 along X3. So along this axis, what is the distance between Z2 and Z3? Since Z2 and Z3 are intersecting, the distance along X3 is going to be 0. So D, so alpha A3 is 0. Next, alpha 3 is the angle between Z2 and Z3 along X3. Okay, but you see that Z2 and Z3 are in the same line. So the angle along X3 is going to be 0. Okay. Next, let's compute what D3 theta 3 is. So I put I equals 3. So 3 minus 1 is 2, X3, C2. So I need to compute the relation between X2 and X3 along Z2. X2 is here, X3 is here, and Z2 is here. So I'll draw that down. X2, X3, Z2. Okay, so to compute D3, it's going to be the distance between X2 and X3 along Z2. Okay, you can see that this distance from here to this point is parameterized by D3. That's the degree of freedom. As the joint moves, that distance will change. So this distance is D3. So D3 is D3, and theta 3 is the angle between X2 and X3 along Z2. Okay, since X2 and X3, or in other words, you need to look at it in this direction. Move this out of the way. You need to take a look at the angle between X2 and X3 from here along Z2. So X2 and X3 line up, which means that theta 3 is 0. So this is the last parameter set, D3 and 0. Let's put it in the table. So 0, 0, D3, 0. 0, 0, D3, 0. Okay, let me check if I got the same in my notes. Yeah, same thing. Okay, so that covers step number 2. We've computed this. The third step is apply the DH transformation, okay, which is this formula. So what I do is, since this is a function of I, there will be a h for each line of this DH table. So for example, if you put I equals 1, you will have h1, 0. That will correspond to this. For the first row of the DH table, when you put I equals 2, it will be the second row of DH table, and there'll be a 3 for the third row of the DH table. So we get that. Then we compute hn with respect to 0. So it'll be h3 with respect to 0. So you'll concatenate all the 3 matrices. And what will come out of it is this 4 by 4 matrix, whose the first 3 rows columns gives you the orientation. The last column, the fourth column, will give you the position of the end effector. So to complete this third step, compute I minus 1 using the TH formula. So that will give you H10, H21, H32. Okay, so get this first. Then we need to compute H30, which will be H10, H21, H32. So you'll multiply these together. When you multiply this, and I'm not doing this step because right now I've not given you any parameters for them. So this will be a big mess of symbolic values, which have no meaning. But if I give you numeric values, then you can actually populate this matrix multiplication. It will come out to be something like this. Okay, in fact, n would be 3. So this part will give you the orientation of the end effector, and this will give you the position of the end effector. Okay, so that will complete the problem. But when you have numeric values, it's much easier than to do it symbolically. So that was another example. Let's do another example of TH, and then I'll give you some I've already posted a whole problem set where you'll get to do this yourself.